Hello there, this is a presentation explaining the research project I have been working on entitled Proof of Identity, a blockchain consensus algorithm to improve Byzantine fault tolerance in swarm robotics. I am Tivianthan and this research project is done in partial fulfillment of the requirements for my master's degree. This is the outline of this presentation. And before I explain my research work, let me explain the problem domain. First, let's try to understand swarm robotics. In swarm robotics, we have multiple simple robots interacting with one another and their environment to collectively solve problems. A good example of this is detecting radiation leakage in a nuclear power plant where a swarm of robots can cover the entire plant and decide if there is leakage. This is heavily informed by nature. Researchers have drawn inspiration from ant colonies, bee colonies, bacterial colonies, etc. Brambilla et al. Classified existing studies on swarm engineering into two major taxonomies, namely methods and collective behaviors. Collective behaviors was further classified into partially organizing behaviors, navigation behaviors, collective decision-making behaviors, and other collective behaviors. Collective decision-making behaviors was again classified into consensus achievement and task allocation. This research focuses on consensus achievement. Consensus achievement is reaching a consensus on one choice among several alternatives. Valentini et al. Further classified this into discrete and continuous consensus achievement. In discrete consensus achievement, choices are finite and countable, whereas in continuous consensus achievement, choices are infinite and measurable. This research focuses on discrete consensus achievement. In order to benchmark different discrete consensus achievement strategies, Valentini, Brambilla et al. Came up with the following collective perception scenario. In this scenario, we have a square grid of area 200 cm square. This grid consists of 400 tiles, each of 10 cm square. These tiles can be either white or black in color. The scenario involves small epoch robots collectively agreeing on the color of the majority of the tiles. To that end, the robots start with an initial opinion. Half of the robots will start with black and the other half will start with white. Then they move around the grid scanning the color of the tiles. The robots calculate the quality of their opinion by determining how long they managed to read the color they were assigned at the beginning. Then the robots disseminate their opinion to other robots while moving around. This dissemination time is proportional to the quality of their opinion. This scenario was used to test the performance of three consensus achievement strategies. These are DMMD, DMVD, and DC. In DMMD, robots read the opinions disseminated by their neighbors and change their opinion to the opinion of the majority. In DMVD, the opinion of a random robot is chosen. In DC, robots disseminate both their opinion and the quality of their opinion. Then, robots pick a random neighbor and compare the quality of their neighbor's opinion with the quality of their own opinion and pick the opinion with a higher quality. Now, let me discuss the research gaps. Even though these strategies helped achieve consensus, they all suffered from the Byzantine problem. Byzantine robots could intrude the swarm and make the swarm come to the wrong conclusion. Strobel et al. Proposed a solution to this problem using blockchain. However, since the default proof of work algorithm was used, this solution was vulnerable to the 51% attack problem and took longer to achieve consensus. The 51% attack problem is a problem endemic to the proof of work algorithm. In proof of work, miners in the blockchain have to solve a puzzle in order to have the blocks they mine get added to the blockchain. This is CPU intensive. An attacker, by introducing a miner that has more than 50% of the total CPU power of the blockchain network, can compromise the reliability of the blockchain. During the literature review, several alternate blockchain consensus algorithms were studied. An ideal algorithm should produce a dynamically permissioned blockchain and allow only authorized miners to mine blocks. Click and practical Byzantine fault tolerance were the only algorithms that came close to the ideal algorithm. Click uses a voting mechanism to add new miners. However, the algorithm does not specify on what basis fellow miners should decide if they should vote in or vote out other miners. Practical Byzantine fault tolerance does not support runtime addition of miners. Next, let's look at the research aim. The aim of this research was to design, develop, and evaluate a new blockchain consensus algorithm to solve the 51% attack problem, allow legitimate robots to engage in mining without affecting the exit probability and the consensus time associated with the proof of work algorithm. This research contributes to blockchain by producing a new blockchain consensus algorithm that would create a dynamically permissioned blockchain algorithm. At the same time, this research contributes to the swarm robotics domain by improving Byzantine fault tolerance in discrete consensus achievement strategies and producing a user-friendly benchmarking tool to perform collective perception experiments. Now that we have looked at the research aim, let's look at the proposed solution. The algorithm developed is called proof of identity. This creates a dynamically permissioned blockchain by using a swarm controller and private public key pair. Let's have a look at the design of this algorithm. This algorithm proposes a novel idea of a swarm controller to authorize miners. These swarm controllers will be able to authorize mining robots so that only these robots will be able to mine blocks in the blockchain. New miners can be authorized by the swarm controller and start taking part in the mining process. First, the swarm controller generates a private public key pair. Then a new robot, before being deployed, requests a signature from the swarm controller by sending its Coinbase, which is its public address. The swarm controller hashes this Coinbase and encrypts it using its private key and returns the signature to the robot. The robot also requests and obtains the swarm controller's public key. Then, during the mining process, the miner seals the block it mined with its signature. A validating robot can get the signature and the Coinbase of the mining robot from the block header and verify the signature using the public key of the swarm controller. If the signature can be verified, then that means the robot has been authorized to mine by the swarm controller. So the block is accepted as valid and added to the blockchain. Since this doesn't involve solving a puzzle, the 51% attack is prevented. Moreover, unlike the proof of authority algorithms where miners are predetermined and cannot be altered or added through a voting mechanism, proof of identity allows authorized miners to be added dynamically in a straightforward manner. Since multiple blocks can be mined simultaneously, there should be a mechanism to pick one block among many. So blocks were assigned a priority based on who mined the block. If the miner has mined blocks previously, then they are given a lesser priority. This priority value was calculated using an offset value. The offset value can be calculated by using this formula. Suppose the number of robots is 10, then we check the last 10 blocks. The offset value for a block reduces as we go back in the blockchain. For instance, if the last block was mined by the miner of the current block, 1 over 1 into 10, an offset value of 10 is obtained. If it was the 10th block, then 1 over 10 into n, 1 is obtained. This gives a higher offset to miners who have mined blocks recently. To prevent the same priority being obtained, a random value is added to the offset value and this offset value is added to the timestamp. The algorithm selects the block with the earliest timestamp. So the smaller the offset value, the higher the priority. This helps us avoid too many branches appearing. The following assumptions were made during the research. A miner authorized by the swarm controller cannot misbehave. Even if a robot is captured, the attacker won't be able to extract the robot signature from the memory. Let's look at the prototype implementation now. Ethereum was used as the blockchain and the consensus algorithm was developed using Go. The swarm controller was also developed using Go and Node.js, React, Redis and Socket.io were used to build the benchmarking tool. This research also produced an application to benchmark using the collective perception scenario. This greatly improved the existing CRUD app, making it more user-friendly. On top of the existing simulator layer and blockchain layer, a service layer was introduced. And a front-end app was developed to allow researchers to design various experiments. These experiments can then be run from the app. A Node.js server is used to store these experiment configurations. The server also runs the experiments by communicating with the Argos 3 simulator. When the experiment is done, the simulator publishes the experiment results to a Redis message queue. The Node.js server obtains this message from the queue and persists the data in a NoSQL database. The app also uses Socket.io to push these results live to the UI. Now, let's have a quick demonstration of this app. Now, this is the benchmarking application that was developed to run experiments. And as you can see, there are three sections. One is the add experiment section where you will be able to design the experiment, and the queue that shows the list of experiments that have been added to the queue, and the experiment data section that will provide you with the results of the experiments. Now, if you don't like this dark view, you can also switch to the light view, and I'm going to show you how to add an experiment first. So I'm going to set the number of robots to 20 here, and I'm going to set the percentage of black tiles to 10, and I'm going to use the direct comparison decision rule, and I'm not going to use blockchain, and I'm going to set the number of Byzantine robots to 0, and I'm going to click on add to queue to add this particular experiment to the queue. Now I can set the number of robots to 10 if I want and add it to the queue as well. So now that I have 2 experiments in the queue, if I want to remove one of these experiments, then I can click on the delete button to delete that experiment. I can also clear the queue by clicking on the clear queue button. Now let me add this experiment again to the queue, and here under the repetition section I'll be able to decide the number of times this particular experiment should be run. So let me run this experiment twice, and when I click on the run experiments button, the experiment would start to run, and the progress bar would show you how many of the experiments have been completed. Now let's wait for the first experiment to be completed, and the experiment is done and we can see the data. Now the second experiment is running. Let's wait till the second experiment is also done. Now you can see the data has been pushed live to the UI using the socket.io library. Now the second experiment is also done, so our experiments are complete and we can see the data here. Now if I want to run another set of experiments, I can design these experiments using the add experiment form, add to the queue, and then click on run experiments to run those experiments. Now what I can do is I can download this experiment data as a CSV file for further data analysis. I'm going to click on this, and the data has been downloaded as a CSV file. So that concludes the demonstration. I'm going to now discuss about the tests that were carried out. Initially, the proof of identity algorithm was compared to the proof of work algorithm. Since swarm robots are low-power devices, Raspberry Pi 3 Model B was used to run these tests. A smart contract with a counter was developed and deployed in a private blockchain. A Web3.js application was developed to increment the counter 100 times. The CPU usage time and the average consensus time, that is, the time taken to increment the counter by 100 times, were used as metrics. When the proof of work algorithm was used, the mining process crashed since the CPU usage was high. However, the test ran successfully when the proof of identity algorithm was used. The average CPU usage was measured to be 79.62%. Since proof of work crashed on Raspberry Pi, tests to find the consensus time was run on a laptop. Proof of work took 3260.7 milliseconds, while the proof of identity algorithm took 3001.37 milliseconds. Immunity to the 51% attack was tested by introducing rook robots with fake signatures. The blocks mined by these robots were rejected by other nodes. Finally, the proof of identity algorithm was benchmarked against the classical solution and the proof of work based blockchain solution. The experiments were run adjusting the difficulty value and the decision rule. The difficulty is the ratio between the number of black tiles and white tiles. 72 experiments were designed and each experiment was run 10 times. The benchmarking used the exit probability and the consensus time as metrics. Exit probability is the number of times the swarm found the correct color out of the total runs. Consensus time is the average time taken to achieve the correct consensus. The findings of this research were consistent with the findings of the previous works. DC performed better than everything else and the performance declined with difficulty. And the classical solution performed better than both the blockchain solutions. However, the proof of identity showed slightly better performance than proof of work, though for most parts they were on par. However, proof of identity performed better than proof of work in consensus time. With proof of identity, the swarm could achieve consensus faster than with proof of work. The test results were consistent with the results of the previous research works. Exit probability was largely unaffected by the proof of identity algorithm. However, the consensus time improved for all cases. Now I am going to discuss the evaluation of the research work. Altogether, 9 experts evaluated the research work. This included Professor Marco Dorigo, one of the pioneering figures of swarm intelligence, and Dr. Volker Strobel, whose research this work is based on. 2 blockchain experts, 4 swarm robotics experts, 2 industry experts, and 1 robotics expert evaluated this research work. Both Dr. Walker Strobel and Professor Marco Dorigo commended the engineering aspect of the research work while being critical of the scientific aspect of the work. Their feedback was important in identifying scientific flaws in the research work and the scope for future work. The following limitations were identified: expecting developers to physically protect the swarm controller from rogue robots, not testing the effectiveness of the timestamp generation algorithm, and not testing this algorithm in a real-world environment. Furthermore, proof of identity's consensus time was much higher than the classical solutions. This research can be further improved by developing blockchain-native decision rules to improve the exit probability. Moreover, more tests need to be done to study the impact of the timestamp generation algorithm, which was used to assign different priorities to different blocks. Further, the proof of identity algorithm can be improved by allowing robots to take turns to mine blocks. Finally, an authorization mechanism can be developed on top of click and stellar consensus protocol, and the performance can be compared to proof of identity. Now let's look at the conclusion. Having to learn Go, the absence of documentation on developing a new consensus algorithm, the steep learning curve associated with swarm robotics, and power cuts that made running tests continuously difficult were some of the challenges faced. Existing skills such as blockchain development, front-end development, and knowledge in concurrent and distributed computing were used in this project. In addition, blockchain consensus algorithm development skills, Go development skills, Argos 3 simulated development skills, and Redis development skills were learned. Next, let me discuss the publications made. A review paper that studies the consensus achievement strategies against the backdrop of swarm robotics and critically analyzes their limitations was written and sent to the Swarm and Evolutionary Computation Journal. This is currently under review. A research paper that dwells on the collective perception experiment carried out using the proposed proof of identity algorithm was written and submitted to the Swarm Intelligence Journal. This is also under review. A research paper that elucidates the proof of identity algorithm and presents the results of the tests carried out against the proof of work algorithm was written and submitted to the International Journal of Blockchains and Cryptocurrencies. This is also under review. A review paper that critically analyzes the application of blockchain in the collective decision-making scenarios in swarm robotics was written and submitted to the Ledger Journal. This is also being reviewed. A review paper that studies the existing blockchain algorithms and their suitability in swarm robotics was written and submitted to the IET Blockchain Journal. This is also under review. Altogether, 5 papers were written, 2 of which are research papers and 3 are review papers. And that concludes my presentation. Thank you so much for your time.